Okay, we're going to work 6.71. We're asked, what is the enthalpy of reaction, or my delta H, for this reaction? Okay. Now, the thing is that we're not given really any information about that reaction. But instead, we're told about this reaction and this reaction. Neither one of these is the same as that one. Now, I know that if I take 1/2 N2, combine it with 1/2 O2 to make this, that's associated with an enthalpy change of 90.3 kilojoules. I also know one of these, half of this, makes this, and that's associated with an enthalpy change of negative 8.6 kilojoules. But neither one of these reactions by itself represent this. However, one of the interesting things that we learn about in this chapter is this business of Hess's law, which basically says that if I can combine reactions of known enthalpy change to yield the desired reaction, I simply need to sum the associated enthalpies of the individual processes to yield the expected enthalpy for the overall process that I want to know something about. So the trick is to take these reactions, rearrange them however is necessary, such that when combined, I can generate that reaction. If I'm able to do that, I can estimate my delta H. And that's going to be my strategy here, okay? Now, how in the world can I combine these two processes to make that one? Let's think about it a little bit. Kind of go through the thought process that you will be faced with when you have to do this type of problem. So the first thing I usually do is try to find sort of unusual reactants or products. Okay, so I look at this molecule and say, oh, that's a little bit unusual. It really only appears one place in one of my equations that I'm given. Okay, and I notice here that it's on the left side of the arrow, it's a reactant, right? And here it's on the right side as a product. Well, that's not going to work. I'm going to have to flip reactants and products for that reaction. So that's going to be kind of one of my first thoughts. So if I did that, I would have NOCl gas, okay, on the left, and that's going to make NO gas and 1/2 Cl2. Now that's just reversing what's the reactants and the products, right? Flipping things around. And of course, when I do that, I'm going to have to flip this delta H. We'll get to that here in a second. But another thing that I noticed before I do that, talk about the delta H value, is that here I've got 2 copies of this, and here I've only got 1. So even reversing the reaction is not enough. I've got to multiply all of the reactants and products by 2. Because instead of having 1 copy, I need to have 2. So I'm going to have to make this a 2, make this a 2, and make this just a 1. Now I'm going to leave that unwritten, okay? So let's think about the sign on delta H for the process that I've just written and what the magnitude of delta H would be for this process that I've just written. Now, this reaction had a negative 38.6 kilojoules delta H associated with it, the enthalpy change. Now, the first thing I did, don't forget, is I flip-flopped reactants and products. When you flip-flop reactants and products, you have to change the sign. So I know that my new enthalpy for this new reaction is going to have a positive sign because I flip-flopped what the reactants and the products are. It was negative, I need to make it positive, okay? That's the first thing. The second thing I did is that I multiplied my reactants by 2, right, to make the stoichiometry work out. When you do that, you also need to multiply the enthalpy by the same factor, okay? So I need to take my 38.6 kilojoules and I need to double it, or multiply by 2, which is going to yield 77.2 kilojoules, okay? 77.2 kilojoules positive. So I doubled it because I multiplied everything by this factor of 2. I reversed the sign and made it positive because I flip-flopped the reactants and products. But the good thing about what I've done here is now I've made my 2 copies of NOCl appear in the right location, okay? And that's usually pretty crucial for figuring out these problems, how to combine the reactions. Okay. Now, the next thing I need to do is consider if this other reaction is important, this first one up here, and if so, how. Okay, so let's think about this for a second. Look for something else kind of unusual maybe to help us. We got these NOs here. Where's NO up here? Oh, there is no NO. Okay, so I need to make the NO kind of disappear, go away, or cancel out, I like to say, right? Let's see. It appears in this reaction as a product, which means it needs to be on this side here so I can get rid of it. And not only does it need to be on this side, I need 2 copies of it. And in my first reaction, I've only got 1 copy. So it seems like maybe what I need to do here is multiply by 2 again and reverse the reaction. Because if I did that, if I multiply by 2 and I reverse the reaction, then I would have, let's see, 2 copies of NO instead of 1. And remember, I'm flip-flopping, right? And then I multiply the O2 by 2, so I'd have 1 copy of that because it was originally half, and I multiply that by 2, that makes 1. Same thing with my nitrogen. I have 1 copy of my N2. If I flip-flop reactants and products and multiply everything by 2, and of course this would still be a gas. I didn't show it, unfortunately, but let me go ahead and do that this time. All right, now what is the enthalpy or the delta H that's associated with this reaction? So what did we do? We multiply by 2 and we reverse. So let's consider the reversal first. If you reverse reactants and products, you change the sign. Right? So instead of having a negative or a positive 90.3, now I'm going to have a negative just by virtue of flip-flopping the reactants and products. But I also multiply by 2. So to compute my new enthalpy expected for this reaction, I need to multiply 2 times the 90.3 kilojoules, and that's going to make 180.6 kilojoules. And it's got to be negative because I've flipped the reactants and the products. You with me on that? All right, hopefully so. So let's see if we've made any headway here. I like to draw almost like an addition sign because I'm going to add the 2 reactions together, combine them is maybe a better word, okay? Now what I'm going to do when I do this is I look for things that cancel out first. So I said I've got 2 copies of NO here, 2 copies of here. In fact, I was very intentional about making the same quantities on both sides of the arrow so that they would be eliminated because there's no NO in my desired equation, right? But what else is there? There's 2 NOCl gas. That comes down, doesn't cancel, it's only appearing in one place, right? I got to bring my 1 copy of Cl2 down. That doesn't cancel. My 1 copy of O2, I'm going to bring that down. And my 1 copy of N2 gets brought down as well. So now what we're going to do is regroup and see how this compares with the desired equation. Where's the desired equation? It's right here, right? So 2 NaCl, okay, 2 NaCl, that's good. We got N2, 1 copy of N2, 1 copy of O2, and 1 copy of Cl. Now notice these are in different order than what it is up here, but that's okay. The exact order you write it in is unimportant. Just as long as you have the right stuff, the right materials, and the right number of copies, you're good to go. So in fact, by combining these equations, I can generate the desired equation. And what Hess's law tells me is that if I want to know my delta H value for this reaction, all I need to do is sum together the processes, delta H, the individual processes delta H. Okay, so what I need to do is 77.2 positive and add that to a negative 180.6, which yields negative 103.4 kilojoules. So as a result, this reaction would have an expected enthalpy change, negative 103.4 kilojoules. I'd expect it to be an exothermic process. All right. All right, so this is an example 671. It's a much more complicated Hess's law problem than 672, which I'm going to try to list on the website first. This is a more difficult thing because you had to multiply by 2, you had to reverse things, okay? But if you can do this, I think that you're capable of working this type of problem on an example.